Hello everyone and welcome to Control Engineering Tutorials. In this tutorial we explain how to check the stability of state space models. In particular, we explain how to test or check the stability of a third order state space model that you can see over here. The whole idea of this video tutorial is to teach you the basics of stability of state space models and how to test the stability by hand. This is a very important skill that you need to learn in order to properly be able to understand the stability concept and to design state space controllers. So here's the problem formulation. You're given a third order state space model and I'm asking you the following question. Is it stable? That is it stable, is it unstable, or is it asymptotically stable, or even marginally stable? Let's solve this problem. Here's a brief summary of the procedure for testing the stability of the state space model. We start from a general form of the state space model given by these two equations. This is the state equation and this is the output equation. Over here, we assume that the state space representation is minimal and that there are no pole zero cancellations. In our last lecture, we explained the eigenvalues of A are actually the poles of the system. This means that the eigenvalues of A determine the stability, and this is a very important conclusion. That is, to test the stability, we need to determine and analyze the locations of the eigenvalues of the A matrix. The B matrix, the C matrix, and the D matrices do not influence stability. So here's the procedure for finding the eigenvalues and for testing the stability. First of all, we need to construct the characteristic polynomial. The characteristic polynomial is computed as a determinant of this matrix. Over here, I is the identity matrix, lambda in the general case is a complex number, and A is our state space matrix. Once we compute the characteristic polynomial, we need to compute the eigenvalues lambda by solving this equation. That is, once we compute the characteristic polynomial, we set the characteristic polynomial to 0, and zeros of this characteristic polynomials are actually the eigenvalues lambda of our matrix A, and that's it. After that, we simply analyze the location of the eigenvalues lambda, and on the basis of their location, we investigate the stability. For example, if all the eigenvalues are strictly in the left half of the complex plane, the system is stable. Or better to say, asymptotically stable. Okay, now that we know the general procedure, let's apply this procedure to this particular example. First of all, we need to construct the matrix lambda I minus A. Let's do that. Over here, lambda is a complex number, and the identity matrix looks like this: 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, next we have minus A, and the A matrix is given over here. It is 0, 3, 1, 2, 8, 1, minus 10, minus 5, and minus 2. Now, as the result, we will have the following matrix. This will be a little bit wider matrix, since we will have certain entries over here that depend on lambda. So let's see what do we have on the main diagonal. On the main diagonal, we have lambda, then we have lambda from this part over here, and we have minus 8. Then we have lambda plus 2. Okay, let's see all of the diagonals. Let's see what do we have here. We have minus 3 over here. Then we have minus 1 over here. Then over here we have minus 1. Then over here we have 10. Over here we have minus 2. And finally over here we have 5. Okay. The next step is to compute this determinant. So let's do that. Here you have to be very careful. We want to compute the determinant of lambda I minus a. Okay, so let's start from this entry. We have lambda multiplying, then we have this entry multiplying this entry, so we have lambda minus 8 multiplying lambda plus 2, and then we have minus this entry multiplying this entry. Since over here we have minus 1, multiplying minus 1 becomes 1, so we have 1 multiplying 5. So we have over here plus 5. Okay, so let's continue. Next, let me just correct this. Next, we need to use this entry. Now, the formula is minus multiplying this entry, so we will have plus 3, since minus multiplying minus is plus, and inside we will have this entry multiplying this entry, so we will have minus 2 multiplying lambda plus 2, and then we will have minus this entry multiplying this entry. Since minus and minus produce plus, we will have plus 1 multiplying 10. Okay. And finally, we are left with this entry. So we have minus 1 multiplying. What do we have over here? We have minus 2 multiplying 5. And then we have minus lambda minus 8 multiplying 10. And that's it. Over here, if you group all the entries together, you will obtain the final value of the characteristic polynomial. I will write it over here in the interest of brevity, and I will skip a few steps, which are very basic steps of grouping different powers of lambda. So at the end, you will obtain lambda to the power 3 minus 6 lambda squared. Then you will obtain minus 7 lambda minus 52. Okay, so this is the final value of the characteristic polynomial. Now, advanced students who took previous classes in control engineering will immediately see that the eigenvalues of this polynomial cannot have strictly negative real parts. That is, this system will not be stable. By just looking at these coefficients multiplying the corresponding powers of lambda. Namely, the first necessary condition for stability is that all the coefficients of the characteristic polynomial are either positive or either negative. That is, the first necessary condition is that all the coefficients multiplying the powers of lambda should have the same sign. Obviously, this is not the case since you have a positive entry over here and the remaining 3 coefficients are negative. This means that the system cannot be stable. However, here we will not use that fact. We will go one step further and we will actually use the Routh-Hurwitz stability test to show that, and later on Routh-Hurwitz stability test will show us that we have actually a single eigenvalue in the right half of the complex plane and the 2 eigenvalues are in the left half of the complex plane. So let's continue. Here is our characteristic polynomial again, and we want to investigate the stability of this characteristic polynomial by using the Routh-Hurwitz stability test. The Routh-Hurwitz stability test consists of constructing the so-called Routh table. So let's do that. The Routh table is constructed by constructing the rows associated with different powers of lambda. We will have lambda to the power 3, then we will have lambda to the power 2, then we will have lambda to the power 1, and lambda to the power 0. And let's construct these rows. Okay, so the first row is, we will have 1, namely, we will put the coefficient over here, which is 1 multiplying lambda. We'll put it over here. Then we will take this coefficient, minus 7. We'll put it here. and then over here we will have 0. Similarly, the second row is, the first entry is -6, the second entry is -52, and the last entry is 0. And all other rows are recursively computed from the first two rows. Okay, this entry is computed like this. It's a ratio of, in the denominator over here we'll have -6, and in the numerator we will have a determinant with the minus sign of the matrix constructed from this column and this column. So we will have 1, -6, -7, -52. Okay, how about this entry over here? Again, it's a ratio of, in the denominator we'll have -6, and in the numerator we will have this column and this column. That is, we will have 1, -6, 0, 0 with a minus sign. And over here we will have 0. Okay, now, obviously this element is 0. However, we need to compute this entry over here. So let's do it over here. Let's see. What do we have over here? We have in the denominator, let me expand this, we'll have -6, and in the numerator we'll have -52, and over here we will have -6 multiplying -7 with the minus sign. This becomes -6 multiplying -7. Consequently, over here we will have -6, and we will have -52 minus 6 multiplying 7. And this becomes, what do we have over here? We will have -94, and inside we'll have a minus, actually 94, divided by -6. So we will have 94 divided by -6. This is actually minus, what do we have over here? We can divide the numerator by 2 and the denominator by 2. In the denominator we will have 3, and in the numerator we will be left with 47. So this is 47 over 3 with a minus sign. And now what we can do over here, to make this table to look nice, I will erase this formula over here and this one. Then over here I will write minus 47 over 3, and over here I will add 0. Okay, perfect. So let's continue. How about this entry? This entry over here will be simply a ratio of, in the denominator we will have minus 47 over 3, and in the numerator we will have a determinant with a minus sign. Over here we'll have -6, then minus 47 over 3, then we will have this column, minus 52, let me nicely write it, and here we'll have 0. And similarly this entry will be 0, and this entry will be 0. Next, we need to compute this term over here. So let's do it over here. Let me just erase the previous part so we don't get confused. Let's see, what do we have? We are computing this entry. In the denominator we will have minus 47 over 3. In the numerator we will have minus 6 multiplying 0 becomes 0, and then we will have, let's write it down, minus 6 multiplying 0 is 0, then we will have minus 52 multiplying minus 47 over 3. This becomes 52 multiplying 47 over 3 with the minus sign. So we'll have minus 52 multiplying 47 over 3. Okay, now we can arrange the terms and make this whole term to look nicer. What do we have in the numerator? In the numerator, we will have 52 multiplying 47 over 3, and in the denominator, we will have minus 47 over 3. I can cancel 47 over 3 with this 47 over 3, so we are left with minus 52. Next, I will erase this formula over here, and then I will simply enter the final value. The final value is minus 52. Okay, now we are ready to apply the Routh-Hurwitz stability test. The Routh-Hurwitz stability test tells us that the system is asymptotically stable if and only if the computed entries in the first column of the Routh table are positive. Obviously, this condition is not satisfied, and consequently the system is not asymptotically stable. In fact, it is unstable. Furthermore, the Routh-Hurwitz stability test can tell us how many poles or eigenvalues of the system we have in the right half of the complex plane. This is determined by the sign change of the coefficients in the first column. Obviously, we have this coefficient is positive, then we have over here sign change. That is, the coefficient goes from positive to negative. This means that we have a single pole or eigenvalue in the right half of the complex plane. And this is very important to keep in mind. Now, if we further analyze the entries, we will see that there are no additional changes in the sign of the coefficients, and consequently, we don't have an additional pole in the right half of the complex plane. Consequently, the poles, or better to say the eigenvalues of the matrix A, look like this. We have one pole over here, and we have two poles in the left half of the complex plane. Namely, what I sketched over here, this is the real part of lambda, and this is the imaginary part of lambda. Since we have only a single pole in the right half of the complex plane, this pole needs to be on the real axis. And since we have two poles in the left half of the complex plane, these poles have to be conjugate complex. And that's it. This system is not stable, and that's the whole story. Simple as that. Okay, that's all for today.